Hello, and today we're going to be looking at 10.6, alternating series and conditional convergence. A series in which the terms are alternately positive and negative is called an alternating series. So let's take a look at some examples of these alternating series. For example, the first one, if we start plugging in n equals 1, we have negative 1 squared, which is positive 1 over 1, so we have 1. And if we plug in 2, it's negative 1 over 2, so that's negative 1/2. And then if n is 3, then we have 1 over 3, so that's plus. And you start seeing that the signs will start to alternate. Okay, positive, negative, positive, negative. Okay, let's take a look at the second one. And this one, if we plug in n is 1, that gives us negative 2 for the first one. N is 2. That gives us 4 over 4, which is 1. So plus 1. If we plug in 3, that gives us negative 4 over 8, so negative 1/2. And this will alternate plus 1/4, minus 1/8, so on and so forth. Okay, the third series, if we plug in 1, we get 1. And if we plug in 2, it'll be minus 2. And then 3 and minus 4. And it'll continue like that. So we see that the first one, this is what we call alternating harmonic series. You'll notice that it converges. Right, if you look at each term, after the first term, each term gets smaller and smaller, and we just alternate signs back and forth. Second one, if you notice, the second one becomes a geometric series. The ratio would be negative 1/2, and you can kind of see it in the formula. Right, so our common ratio is negative 1/2, and so it's a geometric. And then this one would converge as well. This last one, notice how if we look at the nth term is not going to 0, right? This is going to keep getting out of control. Minus 6 plus 7 minus 8, it'll just keep going and going and going. This will diverge. Okay, let's take a look at next slide. So we see from these examples that the nth term of an alternating series is of the form. So these will be the various forms. You could obviously play around with the n's, but this is the form where the u sub n is a positive number, right? So u sub n is always a positive number, and it's affected by this -1 to the n, or -1 to the n plus 1, or -1 to any whatever, variable plus or minus whatever index you decide to put in there. So, the alternating series test states that it converges, right? An alternating series will converge if the following conditions are satisfied. The UNs are all positive. Okay, so as long as you look at the UNs, if you took away the -1 to the power, think of like the absolute value, they're all positive. The UNs are eventually non-increasing, so as we go from one term to the next, they have to be either staying the same or decreasing. Okay, notice the greater than or equal to. Alright, so going this way, they have to be decreasing or staying the same. And UN is going to 0, so that's another way of saying limit as n approaches infinity of UN is going to be 0. Right? So the limit of these UNs is approaching 0. Okay. So let's take a look at our next slide. So if you notice, we have the alternating harmonic series from our first example, where we had the 1 and the -1/2 plus 1/3 minus 1/4. That would resemble this graphic, okay, and it looks like, if we draw out our sum here, it looks like it's approaching ln of 2. Okay, so this one is going to converge. Okay, you'll notice the terms are decreasing as we go successfully. We got the 1/2, 1/3, 1/4, so on and so forth. Right, those UNs are all positive. They're not increasing, and the limit of 1 over n as n approaches infinity, right, would be 0. Right? Okay, so this one definitely converges by the alternating series test. This other graphic shows you if this was non-alternating, right? If we just had positives here, plus 1/2, plus 1/3, plus 1/4, plus 1/5, that we would not converge. This would eventually keep getting larger and larger and larger by small fractions, and this would diverge. Okay, so let's take a look at our next slide. So we have this case, a second way to show that the sequence is non-increasing is to define a differentiable function f of x satisfying f of n equals u to the n, u sub n. Values of f match the values of the sequence at every positive integer n. And then if the derivative is less than or equal to 0 for all x greater than or equal to some positive integer n, then f of x is non-increasing, and then we would show that this sequence this one would converge. So let's see, if we had this, if this were the series, that means our un, this means our un part would be 10n over n squared plus 16. And then they said that we could take the derivative. Okay, so if we take the derivative, okay, so I'm basically going to say that this is a function. Okay, so now let's take the derivative. This would be quotient rule, right? Okay, so let me come back over here. Okay, so quotient rule, denominator times derivative of the top. So that'll be x squared times 10 minus top times derivative of the bottom all over denominator squared. Okay, so does that give us anything? So we have, what do we have here? Okay, so I have 10x squared plus 160 minus 20x squared Okay, I could simplify that a little bit. Come back over here. So it's negative 10, so I have 160 minus 10x squared which means if I could factor out a 10, I would have 10 times 16 minus x squared over x squared plus 16. So now if this is the derivative, it said that if the derivative was less than or equal to 0 for all x greater than or equal to some positive integer n, then f of x is non-increasing for x greater than or equal to n. Okay, so that means if we plug values in here, it has to be less than 0. Well, if we plug in like numbers like 0, that's positive. 1, that would be positive. 2 squared, 4, 3 squared, 9, still positive. 4 squared, that would be 16, so that's a 0. And then we start getting negative after 4. So like 5, right? 5 squared becomes 25, and then 16 minus 25, that's negative. Okay, so this is going to be less than or equal to 0 when x is greater than or equal to 4. So that means that the condition that we want, the non-increasing, we would have the un be greater than or equal to un plus 1 for n greater than or equal to 4. So that means then we could say that the sequence is non-increasing for n greater than or equal to 4. Okay. Alternating series estimation theorem. If the alternating series satisfies the three conditions of theorem 15, then for n greater than or equal to capital N, the sum, S sub n, the sum would be equal to, you see here, u1 minus u2 plus dot dot dot, all the way up to u sub n. This approximates the sum, right? So only it's an approximation. The sum of the series with an error whose absolute value is less than u sub n plus 1, the absolute value of the first unused term. Furthermore, the sum lies between any two successive partial sums. Okay, so we tried theorem 16 on a series whose sum we know. Okay, so this was our geometric series, right? So let's take a look at this example. Let's try to come up with a partial sum here using the estimation theorem, alternating series estimation theorem. Okay, so we see that if we do we got the terms here laid out for us. We got the first term. We know that the common ratio would be -1/2. So that means if we're doing the sum, right, the sum of the geometric series, sum would be a over 1 minus r. So that means it would be 1 over 1 minus -1/2, which means we have 1 over 3/2, which is equal to 2/3. Okay, so that's what it would sum to, 2/3. Keep that in mind. Okay, so now if we do this, that means let's say we're gonna truncate. We're gonna cut off the series after the 8th term, right? So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're gonna keep this part, and we're gonna chop off the 1 over 256. Right? So that means if we add up the first 8 terms, okay, the first 8 terms, add them up, and we would get 0.6640625. If we were to add the 9th term, right, some of the first 9 terms, we would end up with 0.66796875. Okay, so that means our sum of the geometric series, right, the sum that we determined in the beginning, this would have to fall between these two partial sums, right? So we would say that 0.664062 would have to be less than 2/3, and 2/3 would have to be less than 0.66796.875. Okay, so this is good, right? This shows us that this is a good estimate, right? These are good estimates of our sum. And if we were to subtract 2/3 minus the 0.664 0.625, we end up with something that is positive and less than the 9th term, and that's what we wanted, right? So we end up with 0.002 604 1666. Okay, it's positive. And it's less than 1/256, which is 0.00390625. Okay, which satisfies that piece, right? The sum lies between any two successive partial sums, right? So this sum, it's between two partial sums, and the remainder has the same sign as the first unused term. Okay, so the first unused term was positive, right? That's the first unused term, and the remainder, when we subtract the 2/3 minus the 0.664, right, that sign matches the sign of the unused term, so that's good. Okay, so that fulfills the alternating series estimation theorem. Okay, example 4. If p is a positive constant, then the sequence 1/n to the p is a decreasing sequence with limit 0. Therefore, the alternating p series, when p is greater than 0, converges. So, when p is greater than 1, we say that the series converges absolutely. Converges absolutely. And it's an ordinary p series. If p is greater than 0 and less than or equal to 1, then we say the series converges conditionally by the alternating series test. Okay, so a couple examples with that. Let's say p is equal to 3/2, right? So the case when p is greater than 1. So if p is greater than equal to 3/2, we would have 1 minus 1 over 2 to the 3/2 plus 1 over 3 to the 3/2 minus 1 over 4 to the 3/2, etc., etc. Okay, so this would be an absolute convergence. If we said that, let's say between 0 and 1, we said p is equal to 1/2, then we would have 1 minus 1 over square root of 2 plus 1 over square root of 3 minus 1 over square root of 4 plus, and we say that this would be a conditional convergence. Okay. Okay, rearrangement theorem for absolutely convergent series. So if your series converges absolutely and you have b1, b2, bn is any arrangement of that same sequence, then the series with this rearrangement also converges absolutely, and the two series are equal, of course. It's kind of like taking a deck of cards. You're saying that this deck of cards converges absolutely, and now let's say you shuffled the deck. Well, they're the same cards, just maybe in a different order, right? So that new deck that you have after you shuffled, well, that also will be equal to the first deck, so that means it will also converge absolutely. Let's take a look at this example 5. So we know we have the alternating harmonic series converges to some number L. So if we say that by Theorem 16, L lies between the successive partial sums, so the limit does not equal 0, and if we multiply the series by 2, we obtain the series down here. So let's see what's going to happen. So we have 2 times the series, right? So 2 times the alternating harmonic series. So if we distribute the 2, now we get 2 minus 1 plus 2/3. And so now if we were to rearrange in a way, right? Let's see, if we were to take 2 minus 1 minus 1/2 2 minus 1 minus 1/2, so I'm just rearranging them. So I used this one, and this one, plus 2/3 minus 1/3, 2/3 minus 1/3 minus 1/4. So I use 2/3 minus 1/3 and then minus 1/4 plus 2/5 minus 1/5 minus 1/6. So 2/5 minus 1/5 minus 1/6. We continue this fashion plus, what would the next one be? 2/7 minus 1/7 minus 1/8, and this would continue. And what do we end up with? Well, let's simplify what's in the parentheses. So we have 1 and minus 1/2 plus 2/3 minus 1/3 is 1/3 minus 1/4 plus 2/5 minus 1/5 is 1/5 minus 1/6 plus 1/7 minus 1/8 plus dot 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 dot. So we see that we end up with our original alternating harmonic series, right? So we end up with our original harmonic series. So by rearranging the terms of the conditionally convergent series, the series becomes the original alternating harmonic series, and it shows us that we have the same original series. Okay, and so we come up to the summary of tests to determine convergence or divergence. From the last several sections, these are all the tests that we've gone through. Nth term test for divergence, the geometric series, we know when it converges, otherwise it diverges. P series, okay, converges when p is greater than 1. Series with non-negative terms, we try the integral test, or try comparing to a known test with the direct comparison or the limit comparison test. We could also try the ratio or the root test. Series with some negative terms, does it converge by the ratio or root test or by any of the previous tests mentioned above? Remember, absolute convergence implies convergence, and alternating series converges if the series satisfies the conditions of the alternating series test. Okay, so that's it for today's lesson. Any questions you guys could ask me during our meeting on Thursday. Okay, have a good night, have a good day. We'll see you guys later.